What we want to look at is the conservation of linear momentum today. Good. You can see that on screen now. Okay.
Yes.
So what we start with is again our volume, which can change with time. And again, we're going to look at it from a continuum mechanics perspective. So we look like at the small parcel, small volume parcel dV. And now we want to look at momentum, linear momentum. So how is momentum defined?
Mass times velocity.
Yes, exactly. Perfect. So it's mass times velocity. That's linear momentum. Not just momentum in this case. So what would be the total momentum for this body with this volume v here t? So the total momentum. Well, it becomes the integral over the whole volume of rho times the velocity v integrated over the volume. So v, you see again the notation with the bar below v. So v is a vector and rho is density. Shall I write you down this as well? So we have density, rho, and like last time, depends on position x and time t, and then v, velocity. So again, a function of position and time. So now what we're interested in is again the rate of change of that quantity of total momentum. So the rate of change is again the time derivative of total momentum. And this equals
0.
0 if there would be no forces applying onto that body. You have to think, for example, of Newton's law, where mass times acceleration equals to the forces applied, basically. So the same here, so it equals to the applied forces on that body. So we come to these forces in a second then, where we separate the forces into forces which act on within the volume, like a gravity force, for example, and forces which only act on the surface of that body. Like you push, for example, on the body. So an applied force on the surface only. But let's quickly write down this rate of change, total momentum, in form of the equation that we have. So we have d over dt times total momentum, and this is the volume integral of rho times v. velocity. Good. Like last time we saw it, we can basically keep the volume fixed, but then take the derivative inside. So we have the time derivative of this quantity rho times v, dv. And then plus this surface integral, basically, of the quantity rho v times now the velocity field and the normal on the surface. So basically the fluxes. So again, this term you have to think of a flux, basically, which carries the quantity in or out the surface. So this determines basically how much momentum is carried over the surface. So is that clear? From last time, we looked at conservation of mass. We also had these two terms, basically. The part where we looked at the changes inside the fixed volume, and then the flux part, which takes this quantity in or out.
Professor?
Yeah?
I'm just confused by the lower V and the capital V.
Mm-hmm.
So lower V means the velocity, right?
Yes.
And the capital V means the volume space, right?
Yes, that's the volume. Yes, you're right.
Okay.
So this thing here is the volume. This thing here is a velocity.
Okay. So all the V in the bracket are all the lower V. That means
Yes.
the velocity.
Yes.
Okay. Got it.
Good. So again here, the surface integral, we could rewrite it using Gauss theorem or the divergence theorem. So we can put this basically under the volume integral. So this is the volume integral, and we have our time derivative of rho times v plus at Gauss theorem or the divergence theorem that takes now the divergence of this quantity of v times v, and then integrate over the volume. So again, this is a bit a new notation here for this part. It's not a dot product between two vectors, but this is a tensor product or a dyadic product. You have that in the little math PDF as well, distributed for this class. So this is a notation for tensor product. And if you want in index notation, sometimes that helps to see what these terms are. So in index notation, this would look like the integral dt rho vi So the I component of the vector plus then the divergence becomes nabla j times rho vi vj. Again, this here is the tensor product. And when we repeat the index, so here j is repeated on nabla j and vj, which means that we sum over the index. That's the Einstein summation convention. So if repeated indices basically means summing over the repeated index. It's like here, summing over j. But using Einstein summation convention, this can just be written short that way. So tensor product, think of it as using two vectors and constructing a matrix with these two vectors. So if we, sometimes you see a symbol like that for the tensor product. We use it like this without the dot. Index notation is vi times vj. So it's now basically a matrix where you have v1 times v1, v1, v2, v1, v3, these products. And for three-dimensional vectors, it's a 3 by 3 matrix, basically. And we have v3, v2, v3, v3. Did you see this tensor product already or not yet? Something new? Good. But is it clear with the index notation what we mean by this term with the tensor product?
Yes.
Good. So now let's come to the forces. So what we had is basically the rate of change of momentum is equal to the forces. And the forces we split up now into body forces, which act on the volume, within the volume, and the ones which only act on the surface. The forces which only act on surfaces are attractions. So think of here as being the body forces. For example, gravity acts within each parcel of the volume. And then here the tractions. Only forces you apply at the surface. So if you have the volume here, body force can attack within the volume, where attraction only applies to its surface. So I'm not sure if you heard this term traction already and you know how it's related to the stresses. So let me quickly write that down. So the traction we write here is a vector t. And it's related to the stress tensor t by taking the stress tensor and take the dot product with the normal at the surface. So small t is the traction, so vector quantity, and capital T here with 2 bars is the stress tensor. So now you see again a new notation with 2 bars instead of 1 bar. And 2 bars means a tensor, 1 bar means a vector. So T is T11, T12, T13, etc. So it's a 3x3 vector, tensor, sorry. So we just write 2 bars below it. That sense, it's a second order tensor. We come to that later when we come to the elastic tensor. The elastic tensor is a 4th order tensor. So we will then put 4 bars below the elastic tensor. So maybe in index notation again, let me put that here. It's just the I component would be the product Tij times Nj. And again, you see we repeat the J index. So it would be summing over J. Again, with the summation convention. So if you see repeated indices, means we take the sum over that index. Good, it's just a notation. Playing around with the notation and trying to understand it. Now again, if you look at the forces, we have the body forces as a volume integral, the traction as a surface integral. And by now you know that we want to put it under the same integral basically. So we again apply Gauss theorem here for the tractions. So when we do that, let's write that down. So how to go from the surface integral of the tractions, which we can write now as the surface integral of the stress tensor dotted with the normal. And now we can use Gauss theorem again to write this as a volume integral. And this time the divergence of the stress. Now it has become a volume integral. So again, this one is due to Gauss theorem. Or if you want, they're also called divergence theorem. So a little exercise for you. What would be the index notation of this volume integral? So volume integral, and now nabla
J.
Times T.
Ij.
Yes. So that would be index notation. And again, we would sum over J. So again, think of having the sum over J in front. So is it clear so far? So now you see we put down the forces, the applied forces. And now we just want to bring it basically back into the rate of change of total momentum. So we'll write this all down, basically the rate of change of total momentum equals to these applied forces. So let's do that. So now we find that we have the integral, the time derivative of rho v plus the divergence of vv dv. This is our rate of change of total momentum, is equal to the applied forces, which is the volume integral F plus now the divergence of the stress dv. So on the left side, you see the rate of change of total momentum. And on the right side of the equation, you'll see the applied forces. So this is again valid for any volume. Whatever Vt we set out at the beginning, this equation is valid, so which means that therefore the quantities inside the integral have to be equal. So we have now the rate of change rho times v plus the divergence of this rho vv, and we can bring over the stress tensor, so we have it in the same divergence. It's equal to the force F. Good, so this is basically a conservation of momentum, what we just wrote down now. Or if you want linear momentum, let's just call it momentum. So is it clear how we came to that equation?
Yes.
Good. So we looked at linear momentum, how it's defined. We look at the rate of change, the total momentum, which equals to the applied forces on that volume. And if we write this down, what we end up is this equation. The conservation of momentum. Good. Let's quickly compare with the mass conservation that we saw last week. So just a little excursion, compare with mass conservation. So last week we saw that the conservation of mass leads to the continuity equation. And the continuity equation we wrote as the rate, the derivative with respect to time of density plus the divergence of rho times v was equal to 0. So if you compare the two equations, they look very similar. What you have is something where we have the rate of change of a quantity plus the divergence of the quantity is equal to something. So this is a typical form of a conservation law. And you will see that the quantity that we mentioned here can be density, for example. Then we have conservation of mass. It can be momentum. Then we have conservation of momentum. And we keep on doing that with angular momentum and with energy. Good. So that was just a little excursion. So let's write down again the conservation of momentum. And like last time where we switched basically the perspective from a Eulerian to a Lagrangian perspective, we do it for the conservation of momentum as well. Let's see what we end up with. So let's write out the conservation of momentum from above. So with this time derivative plus the divergence yeah, let's keep it this way, minus the stress tensors equal to the body forces. So what we use now basically is to simplify this divergence term. So we can rewrite this part a little bit. And you can try and sit down and figure that out. I just write it down for you here. So we end up with terms where we have V times the divergence of rho V plus rho V dotted with the grad V minus the last term we end up with is the divergence of the stress. So let's put that again into the above equation. So we have first term doesn't change. Oh, we can, yeah, let's take density in front here. So let's write this term. So when we take the time derivative of the first term, we can split it up into two terms. We have the first term is rho times the time derivative of v, plus then the second term would be v times the time derivative of rho. Is that clear?
Yes.
Good. So what I will do is I will put these terms a little bit together so that things then become a bit more clear. But this would be basically the second term. So v times now the time derivative of rho. But again, we have another term with v in front. So here now we have the divergence of rho v term. Oops, how can I show you that? So this term here would be going into here.
Wouldn't it be negative?
Right, yes. Let me think. No, it's plus. So here it comes basically from this term here. So we just replace all this expression with this one here. And then this, the first term is still positive. So it's still plus. Now let's remove these things. Okay. Then come the additional term with rho v. So this is green. This term. And then minus the divergence of the stress equal to F, body forces. Okay, now the whole exercise, why we rewrote it this way, is because of this term here. So look at the typical form of the conservation law for mass, which we just wrote above. So what we see here is basically the conservation of mass, or if you want, the continuity equation, which means that this term vanishes, so it's equal to 0. So that allows us to simplify a bit now the above equation. So let's do that. We have rho times time derivative of v plus velocity v dotted with the gradient of v, grad v, equal to the divergence of the stress plus the body force F. Okay. And now this, if you look at the material derivative, this is the material derivative dt of the velocity v. So we have rho dTV is equal to the divergence of stress plus F. Okay. So this again is conservation of momentum, this time written from a Lagrangian perspective. We use the material derivative. So the question is, can we solve this equation? So let's forget about the dimensions. Let's just assume it's 1D. Then the vector becomes a scalar. The tensor becomes a scalar. So then at the end, we have one equation. And which ones are the unknowns? Or which ones are the knowns? Let's start with the ones we can set.
Density is known.
Density is known. So this thing here is known. This is V, the velocity. Is unknown. T, the stress. Is unknown. The force we can set. So the source we can set at the beginning is defined and density is defined. So the unknowns here is the velocity and the stress, which basically means we have one equation with two unknowns. So there's no solution yet for that equation, which means we need something more. And that's the constitutive law that comes now into play. So what we do is basically we link the stress to the displacement, which is linked to the velocity. So this equation needs a constitutive law to solve. And what's the constitutive law here that links stress to displacement? That's basically Hooke's law that comes now into play. You're probably familiar, Hooke's law is not really a law, it's not a conservation law, which is a physical law. Hooke's law is only a constitutive relation for elasticity, which links the stress tensor, Tij, to the strain tensor by the elasticity parameters. It'sCijkl times epsilon KL. So epsilon is the strain tensor. C is the elastic tensor. And T you saw before, that's the stress tensor. So Hooke's law relates stress to strain. And instead of index notation in a vector notation, we use these bars basically. So we have a fourth order tensor with 4 bars. And then the double dot product with the strain tensor. So we can write it in this form. Good, that's our constitutive law that we need. Now we can solve the conservation of momentum. But before we do that, we start linearizing the terms. And to linearize, we set out like a small perturbation to a reference density. Let's assume we have a reference density, which doesn't change with time, only with position. Let's see, position is also a vector. And then we have small perturbations with respect to that reference density with time. And these we consider to be small. Good, and what we also use is velocity, which we can write as the time derivative of displacement s. So s here is displacement. So when we do that, we find basically our terms with rho 0, the second time derivative of displacement, equal to the divergence of the stress, plus f. Where we can write the divergence of the stress, we can write in terms of using Hooke's law in terms of strain. So again, we have the time derivative displacement is now equal to the divergence of the elastic tensor dotted with strain plus f. Good. And these are the so-called equations of motion. And what we did is we linearized around rho 0, a density which doesn't change with time. So in 3D, these are 3 equations, the so-called equations of motion. And what is often forgotten, it's linearized in rho 0. So if you want in index notation, sometimes that helps. See what these terms are. Would have rho, time derivative of the I component of displacement, is then this nabla j timesCijkl times epsilon kl plus fi. And here you see we have repeated indices kl, so this is two sums over k and l, and then have a repeated index on j, again another sum. So here we would have sum over j, here a double sum over k and l. And in short notation, it looks like this. So why can we solve now here the equations of motion? So the only thing I didn't wrote down yet is strain, how we define the strain tensor. But if you want, we can define strain in a symmetric way, and in seismology often strain is defined as 1/2 grad S plus grad S transpose. So that basically brings us now from strain to displacement. And if you look now at the equations of motion, the only unknown is the displacement, where density, the elastic tensor, and the forces F, they are all known basically. So we have then in 1D, let's write that down as well. So the 1D equation, what we end up is basically the wave equation in 1D, which is that rho times second order derivative of displacement is equal to the divergence, and in 1D this basically shrinks down to this expression plus F. So the elastic tensor basically only becomes one factor. Here we take mu, for example, which would be the shear modulus. So we have S is displacement. Sometimes we also use U for that, but let's use S here as displacement. Mu would be the wave speed, or if you want, the shear modulus. Then we have a shear motion, and F would be the source. Good. So do you see how the equations of motion become in 1D this expression, the wave equation here? The first term is obvious, the left-hand side of the equation. the right-hand side, if you write it down in 1D, and if we use for strain the definition I put here, the symmetric definition of strain, and this shrinks down to the expression that we have here. So when we solve then the wave equation, what we have to think about is how we approximate these derivatives, the second order time derivative and this first order derivative with respect to space. So these derivatives we will now approximate by a numerical scheme using the finite differences. So is it clear so far how we came to that wave equation?
Yes.
So we looked at the conservation of linear momentum. The rate of change of total momentum is equal to the applied forces. If you want, think of Newton's law, where mass times acceleration equals to the forces, total forces. Then we split up the forces into body forces and tractions, and then ended up with this conservation of momentum equation. Here we can rewrite this a little bit in terms of the material derivative. It's again a conservation of momentum equation, just written using the material derivative. And in order to find solutions to that, we need a constitutive law, which in our case, when we use elasticity, links the stress tensor to the strain tensor, where the strain tensor depends on the displacement. And then we linearize the conservation of momentum equation. It would be non-linear because density itself would be affected. It would also allow to change. If we start linearizing that, we end up with the equations of motion, which then lead to the wave equation. So most of the time in seismology, we just encounter the wave equation. So keep in mind that's a linearized equation of motion. Because in principle, density itself would be affected by the wave propagating through a medium. But we assume that these perturbations are small, the density, by the motion, by the seismic wave that propagates through the medium. So we linearize these terms, all the terms which would have like second order terms with these small perturbations we cancel out. What we're left with are the equations of motion linearized in rho zero. And in 99% of your time, you will see these equations in seismology. Good. So in this class, we will look at this 1D equation, the wave equation in 1D, and now numerically solve this 1D equation. And in order to do so, what we first start with, finite difference approximations, they approximate these derivatives. The second order derivative with respect to time, and the first order derivatives with respect to space. So clear? Things are clear so far?
Yes.
Okay. basically that's what I wanted to come to today. If you want, I can quickly introduce some of the finite difference schemes now, then we don't have to do it tomorrow. And tomorrow we will look at the conservation of energy. And then we come basically to the heat equation. And the heat equation will be the first example, the first homework that we're going to solve with the finite difference schemes. So since we have a bit more time now, we have, let's say, 10, 15 minutes more.
Yes.
So let me put down the finite difference schemes that we're going to use now. So with finite differences, we are going to approximate these derivatives, these differential operators, numerically. So for the finite difference method, so let me start a new page here. So that's our first method that we will look at. So the finite difference method. And when we use the finite differences, then we approximate the derivative. Let's say the spatial derivative. In terms of small steps in space, delta x, of a function f of x. And to find now schemes for finite difference method, it becomes useful to look at the Taylor series of that function. So the Taylor series for the function f around the point x0 expands into the following. So we have fx plus delta x using the Taylor series. We can write it as f of x plus the delta x times the first derivative of f of x plus the second order derivative times delta x squared, and so on and so on and so on. I assume you're familiar with the Taylor series, so this shouldn't look too new to you. And obviously we can do the same, but around x minus delta x. So then again, we start with fx. Now we change the sign, minus delta x, the first derivative of the function, plus again the second order term, minus, etc. So we have these sign changes. Good. So with these two Taylor series, we can basically now, like a cook recipe, come up with different schemes. And the first one we're going to look at is the forward scheme. Where we take the derivative approximated by fx plus delta x minus f of x divided by delta x. So take the the first Taylor series. So it's based on 1 basically. And then what are the terms that would follow? If you look at the Taylor series, well, the next term would be this 1/2 delta x times the second order derivative of f of x, and so on. So the forward scheme only takes the first term, and the rest we're going to ignore. And that's basically the approximation error that we're going to do with the forward scheme. And so this error is called the truncation error. If we leave out all these higher order terms, and if you look at the order of this truncation error, the order that we have is of changes with delta x. So if we choose delta x larger, then the truncation error also changes linearly with that delta x step. Okay, let's do the same, but with the second equation, then it becomes the backward scheme. So again, we have an approximation for the derivative that we're looking at. And this time is backward, so the step is x minus delta x over delta x. And then what are the terms left that we truncate? Again, is 1/2 delta x f double prime of x minus etc. And if we leave out all these higher order terms, again, the truncation error that we're going to do behaves linearly. The error of the order of delta x. It's good so far?
Yes.
Good. Then there are 2 more schemes. One scheme, let's go again for the first derivative. If you want to approximate the derivative f prime of x. And instead of just using one or the other Taylor series expansion, we basically look at both of them. And so what we come to is basically a central scheme, sometimes called central, sometimes called center scheme. You see both expressions. So a center scheme for the first order derivative we can define as x plus delta x minus f of x minus delta x divided now by the step size is 2 times delta x. And then what terms are left?
1/3 factorial.
Exactly, 1/3 factorial. And what is interesting now, we have a term that depends on delta x squared. Then comes the third order derivative of f of x plus additional terms. So if you look at now the truncation error that we're going to do, for the central scheme, it depends now on delta x squared. So we can say here truncation error, when we ignore these higher order terms, changes in this case with delta x squared. And so we say the first two schemes, the forward and backward scheme, are first order schemes because the truncation error changes of delta x. And this central scheme is now a second order scheme where the truncation error changes with delta x squared. So the order of the scheme increases now for the central scheme. So if delta x is small, then a higher order scheme has a smaller truncation error, basically. Good. You also see that the central scheme we can use for the second derivative. So these are approximations for the first order derivatives. And we can do so as well for the second order derivative. Again, using a central scheme. And we look at the second order derivative, f double prime of x. So we can write this down as fx plus delta x minus 2f of x plus f of x minus delta x divided by delta x squared. Plus now the truncation error is 1 over 4 factorial, and then we have x squared times the fourth order derivative of x plus additional terms. And again, you see the truncation error here has an order of delta x squared. There's a second order scheme as well. And so with these four schemes, we can already solve, for example, the wave equation. You see, we would have a second order derivative with respect to time and first order derivatives with respect to position. And with these schemes, we can approximate these derivatives now. So we have different options for the first order derivative, and one here is given for the second order derivative. So we're going to use these schemes and see if we can solve now then the equation numerically. And it's basically up to us which scheme we want to use. We can play around with using what scheme together with which one in order to solve the equations. And that's exactly what we're going to do basically. We play with different schemes, approximate these derivatives, and see if then we can solve the equation numerically. So let's come to that then in the next lecture. For now, I would say let's leave it here. Let's stop here. We saw conservation of momentum or linear momentum, how it leads to the wave equation. And we have now these different finite difference schemes that we can use to solve it numerically. What I want to do tomorrow is basically look at conservation of energy, so we can derive the heat equation. And then we start with the heat equation and use these finite difference schemes with the heat equation to solve that one. That's what we're going to do tomorrow. For today, is there a question on these schemes or on the derivation of the wave equation? Everything clear so far? Good.
Yes.
Good. Let's leave this here. We see each other tomorrow again, same time, same online room. And then I just wish you a good day for today. Enjoy your day.
Thanks.
Or your night, in your case, Faustino. Get a good night's sleep, yes.
Thank you so much.
Good. Thanks for showing up. See you tomorrow.
Yeah, thank you, Professor.
Thanks, sir.
Bye, everyone. Bye-bye.
Bye. Thank you.